Hello everyone, welcome back to this video. The subject is cryptography. The subject code is 21UC642. Now we are
In this module, we are going to discuss about principles of public key crypto systems, under which we'll get to know about public key crypto systems and some of the applications for public key crypto systems, requirements for public key cryptography, public key cryptanalysis. And we also discuss about RSA algorithm, description of the algorithm, computational aspects, and the security of RSA. After that, we'll discuss about some of the algorithms like Diffie-Hellman key exchange, under which the algorithm, the key exchange protocols, man in the middle attack. We'll also discuss about elliptic curve arithmetic, which consists of abelian groups, elliptic curves over real numbers, elliptic curves over ZP, elliptic curves over GF of 2M. So GF of P we have already discussed in the previous module. Here we'll discuss about GFF of 2M, that is Galois field. Here GF stands for Galois field. Elliptic curve cryptography, analog of Diffie-Hellman key exchange, elliptic curve encryption decryption, security of elliptic curve cryptography. And these are the textbooks to be referred. So all these concepts are covered in the first textbook, William Stallings. For better understanding and for more information, we can refer the remaining textbooks also. So today we'll discuss few concepts of about public key crypto systems. So some of the development of public key cryptography is the greatest and perhaps the only true revolution in the entire history of cryptography. So from its earliest beginnings to modern times, virtually all cryptographic systems have been based on the elementary tools of substitution and permutation. After working with algorithms that could be calculated by hand, a major advance in symmetric cryptography occurred with the development of the router encryption or decryption machine. So the electromechanical router that enabled the development of friendishly complex cipher systems. With this availability of computers, even more complex systems were devised, the most prominent of which was the Lucifer effort at IBM that culminated in the data encryption standard. But both router machines and DES, although representing significant advances, still relied on the bread and butter tools of substitution and permutation. Here, public key cryptography provides a departure from all that has gone before. For one thing, public key algorithms are based on mathematical functions rather than on substitution and permutation. More important, public key cryptography is a asymmetric, involving the use of two separate keys in contrast to symmetric encryption, which uses only one key. The use of two keys has profound consequences in the areas of confidentiality, key distribution, and authentication. And there are several common misconceptions about this concerns of public key encryption. One such misconception is that public key encryption is more secure from cryptanalysis than is symmetric encryption. In fact, security of any encryption scheme depends on the length of the key and the computational work involved in breaking a cipher. So there is nothing in principle about either symmetric or public key encryption that makes one superior to another from the point of view of resisting cryptanalysis. A second misconception is that public key encryption is a general purpose technique which has made symmetric encryption obsolete. On the contrary, because of the computational overhead of current public key encryption schemes, there seems no forcible likelihood that symmetric encryption will be abandoned. as one of the inventors of public key encryption has put it, the restriction of public key cryptography to key management and signature applications is almost universally accepted. Finally, there is a feeling that key distribution is trivial. When using public key encryption. This is compared to the rather cumbersome handshaking involved with key distribution centers for symmetric encryption. In fact, some form of protocol is needed, generally involving a central agent, and the procedures involved are not simpler nor any more efficient than those required for symmetric encryption. So here in this module, we'll discuss about overview of public key cryptography. First, we'll look at its conceptual framework. So the concept for this technique was developed and published before it was shown to be practical to adopt it. And then we'll examine about this RSA algorithm, which is the most important encryption or decryption algorithm that has been shown to be feasible for public key encryption. And other important public key cryptographic algorithms are covered in the next topics. So some of the terminologies. So before we start with the principles of this public key crypto systems, we must know about some of the terminologies that is related to this asymmetric encryption. And one such terminology is asymmetric keys. Two related keys, a public key and a private key, that are used to perform complementary operations such as encryption and decryption, or signature generation and signature verification. Public key certificate. So it's a digital document issued and digitally signed by the private key of a certification authority. So that binds the name of a subscriber to a public key. The certificate indicates that the subscriber identified in the certificate has sole control and access to the corresponding private key. Public key cryptographic algorithm, or it's a symmetric cryptographic algorithm. A cryptographic algorithm that uses two related keys, a public key and a private key. The two keys have the property that deriving the private key from the public key is computationally infeasible. Public key infrastructure, a set of policies, processes, server platforms, software and workstations that is used for the purpose of administering certificates and public private key pairs, including the ability to issue, maintain and revoke public key certificates. So the concept of public key cryptography evolved from an attempt to attack two of the most difficult problems associated with asymmetric encryption. The first problem is that of key distribution. So key distribution under symmetric encryption requires either the two communicants already share a key, so which somehow has been distributed to them. The second one is the use of a key distribution center. Like Whitefield Diffie, one of the discoverers of this public key encryption, along with Martin Hellman, both at Stanford University at the time, reasoned that the second requirement negated that very essence of cryptography, the ability to maintain total secrecy over your own communication. As Diffie put it, what good would it do after all to develop this impenetrable crypto systems if their users were forced to share their keys with a KDC that could be compromised by either burglary or subpoena? And the second problem that Diffie pondered, and one that was apparently unrelated to the first, was that of digital signatures. If the use of cryptography was to become widespread, not just in military situations but for commercial and private purposes, then electronic messages and documents would need the equivalent of signatures that is used in paper documents. So that could be a method which can be devised that would stipulate to the satisfaction of all parties that a digital message had been sent by a particular person. This is somewhat broader requirement than that of authentication and its characteristics. which should be explored. Here, Diffie and Hellman achieved an astounding breakthrough in 1976 by coming up with a method. What is a method that addressed both problems and was radically different from all previous approaches to cryptography? So, going back over 4 millennia. So, in this public key crypto systems, asymmetric algorithms rely on one key for encryption and a different but related key for decryption. These algorithms have the following important characteristic. It is computationally infeasible to determine the decryption key given only knowledge of the cryptographic algorithm and the encryption key. In addition, some algorithms such as RSA also exhibit the following characteristic. Either of the two related keys can be used for encryption with the other used for decryption. A public key encryption scheme has 6 ingredients. So here we have a figure which is consisting of a plain text. This is the readable message or data that is fed into the algorithm as input. Encryption algorithm. So encryption algorithm performs various transformations on the plain text, public and private keys. This is a pair of keys that have been selected so that if one is used for encryption, the other is used for decryption. The exact transformations performed by the algorithm depend on the public or private key that is provided as input. Ciphertext is the scrambled message produced as output. Depends on the plain text and the key. For a given message, two different keys will produce two different ciphertexts. Decryption algorithm. This algorithm accepts the ciphertext and the matching key and produces the original plain text. The essential steps are the following, like each user generates a pair of keys to be used for the encryption and decryption of messages. Each user places one of the two keys in a public register or other accessible file. This is the public key. The companion key is kept private as suggested in the figure. Each user maintains a collection of public keys obtained from others. If Bob wishes to send a confidential message to Alice, Bob encrypts the message using Alice's public key. When Alice receives the message, she decrypts it using her private key. No other recipient can decrypt the message because only Alice knows Alice's private key. So, with this approach, all participants have access to public keys and private keys are generated locally by each participant and therefore need never be distributed. As long as the user's private key remains protected and secret, incoming communication is secure. At any time, a system can change its private key and publish the companion public key to replace its old public key. So there are some of the important aspects of the symmetric and public key encryption. To discriminate between the two, we can refer to the key that is used in symmetric encryption as a secret key. The two keys used for a symmetric encryption are referred as public key and the private key. Invariably, the private key is kept secret, but it is referred to as a private key rather than a secret key to avoid confusion with symmetric encryption. Now, let us take a closer look at some of the essential elements of this public key encryption scheme. So, there is some source A that produces a message in plain text, which is consisting of x is equal to x1, x2 till xm. The m elements of this x are letters in some finite alphabet. The message is intended for destination B. B generates a related pair of keys, that is a public key, which is denoted as PUB, and a private key denoted as PRB. PRB is known only to B, whereas PUB is publicly available and therefore accessible by A. With the message X and the encryption key PUB as input, A forms the ciphertext. Let us assume that let the ciphertext be Y is equal to y1, y2 till yn. So we can write this as Y is equal to encryption of PUB X. The intended receiver in possession of the matching private key is able to invert this transformation as X is equal to decryption of PRB Y.